So the model that we are starting today is called deep learning and its variants, right? I am Siddharth. I'll be doing the full module this time, both the theory and the lab versions of it. Um, my background um, is clinical vision science. I did my basic training in something called optometry, which is a health science kind of a degree. Then I moved on to my PhD was in cognitive neuroscience. And then I had like a backdoor approach into neural networks um, around the 2019, 2020 timeframe. When neural networks were the thing to do in the field of AI. And since then, I've been in the field of AI actively consulting projects, teaching, university teaching, corporate teaching, teaching at different domains. Uh, my project has largely been, what to say, the cognitive aspects, how we can leverage the power of LLMs for text analytics, how we can leverage the power of neural networks to understand the brain, and also some consulting projects where I worked in you know, fraud detection in uh, what are called LLMs and SLMs, small language models. So that's been my recent foray. And I've been actively teaching, in the sense, training corporates to use the power of LLMs in the form of RAG and other enterprise level solutions. Right. So that's, I think, enough about me. Uh, Hopefully, you're convinced that I'm eligible to take this module, right? Um, so before we go further, let me very quickly. Uh, I've delivered this particular module in the past, like I think for some cohort 3 or 4, I'm not sure. Some of them are my DBA mentees. So I'm mentoring some of the projects who participate in previous sessions. Um, so hopefully the association will continue if my hands are not full. My DBA project guidance is mostly in the healthcare sector. I'm guiding multiple DBA projects currently. A few on diabetic retinopathy detection. A project which just got completed, and others on dermatology related projects on the business aspect of adopting LLM in practice. So yeah, so various different domains, largely very clinical to very business oriented, thesis to business plan. So I think I'm doing 4 or 5 currently. Um, okay. My association with BBA has been pretty long again. Some of these students get converted to my as my into project guidance. The module is called Deep Learning and its variants. This particular the first session, I don't know, might be a small session. We might end early, but not so in other sessions. The purpose of today's session is largely to convince the audience that neural networks are still worth studying. Now, why do I say this? ChatGPT has created this big buzz over the last couple of years, probably from 2022, and being really, really popular for the past 2 to 3 years. Now, If you ask ChatGPT to perform a task, it probably does the task really well. Some of these tasks actually were the foray of neural networks. So a persisting question in a number of these situations is, are neural networks really worth it? In the sense, the capabilities of neural networks as it was in maybe 2018, 2019, the tasks which neural networks did very nicely, people were behind these neural networks. Are they still relevant in the age of LLMs, right? LLMs, Gen AI, and all that. That's a question that keeps coming to me in a lot of my trainings. And a significant portion of my training, I actually tried to spend convincing my corporate learners that you don't have to do LLMs for everything. You don't have to do Gen AI for every little task that needs automation. So today's session is mostly focused on why LLMs, why neural networks are still relevant in the age of Gen AI when LLMs can do half of these jobs. Okay. If any of the terms that I say now is unfamiliar, please feel free to unmute and ask questions. You don't have to wait till the end of the session. I prefer if you unmute and ask questions or if you type your questions in the chat right away. Are you allowed to unmute? Do you have permission to unmute?
Yes, sir. Yeah.
Okay, nice. So if there is anything, please unmute and ask questions right away. You don't have to wait till the end of the session. Put your questions in the chat box. If any of the terms that I use currently, if they are not familiar, please ask for clarification. And assuming that, these terms that I'm using, LLM, Gen AI, or all have become more or less general purpose nowadays. So everybody uses these terms. And I'm assuming that um, the majority of this audience is familiar with these terms. Okay, so that's going to be the focus of today's lecture. We will probably just start neural networks today and close it. That doesn't mean that the session is going to be lightweight. In the sense, you might have to carry the implications of what we learned today throughout the module and probably keep it in the back of your head that neural networks and studying neural networks is still relevant in 2026. That's the message I want to drive. And as always, we're not going to just believe me, bro. I'm going to try to convince you that my statement is backed by data and it's not just a whimsical thing that I'm saying. So before we go further,
I
hi.
I always assumed or associated neural networks with current AI models, but you're
Yes.
drawing this distinction
Oh,
between the
yes.
artificial neural networks and
Um,
Gen AI. What is it? The distinction.
okay. Okay. So when I say distinction, I'm not saying in terms of the architecture, I'm saying in terms of its application. In terms of if there's a given task, the same task can be accomplished using neural networks. The same task can also be accomplished using LLMs, as we will observe in today's session,
Okay.
right? So that's the distinction I'm making. I'm not making a distinction in terms of its essence or in terms of its architecture.
Okay, thank you.
It's a very good question. Yes. Okay. So I hope you can see the full screen version of the presentation. So where exactly are we in the DBA journey? I'm assuming that some sort of an ML, like logistic regression, linear regression, um, what else? Gradient boost, XG boost, random forest. All these have been covered in some sense.
Yes.
Okay. Um, and this is a really early part of your DBA, right? Where you're still doing your course, but probably your first year, and you're taking multiple courses. And the concept of Gen AI has not been completely introduced. That's my assumption. Yeah, Prince Dubey. Yeah.
Has a so
Hi.
oh,
You can call me
am I audible
Siddharth.
properly? Am
Yes,
I
you are
audible
on board.
properly? Yeah.
Yes.
So my question would be around the mathematics that we have gone through with the with the module that we have already covered in the ML side. And
Okay.
I know in the deep learning side, this is again going to be very vast. So before starting this session, I would like to know that how we should cover the mathematics part as well, because I'm still going through the mathematics that we have already covered into ML side, and I'm finding it's difficult to cover everything in a very small period of time. I know we started ML in March 1st, and now we are into start of May, and still there are a lot of concepts which where still I need to be very comfortable. Although I made a good progress, but I still find a lot of areas where I feel I'm still not very convinced about in terms of my preparation. So deep learning, I know again there will be a lot of myths, so how our approach should be to understand this properly.
Okay. So that's a very reasonable expectation to fear. Deep learning is, as you said, very math heavy. We are going to cover concepts like gradient descent, back propagation, and I'm going to throw all these terms at you. Okay, but what I do hope is I will keep it application oriented, and I will also keep the math simple in the sense I will explain the math using small numbers and using simple architectures, maybe three or four multiplications, like x into y into z, not more than that. But I would want you to imagine the scale and the amount of computation required at scale, right? I would leave that to your imagination. But I will do a little bit of math, but I will try to not keep it math heavy. Okay. I will try to keep it more application oriented in the sense, if I say, okay, if this is happening, then imagine what would be the implication of this, right? Probably at scale. That would be my expectation. I will talk math. I will talk arithmetic. I'll show some sigma. All those formulas which we were scared of in our high school and middle school. But I wouldn't expect you to really work out the math. I'll probably explain the math in English, right? Is that a simple, agreeable thing? Yeah, great. Okay, nice. So where we are in the DBA journey, I think the ML part is done. The LLM, the Gen AI, the real emerging technologies have not been introduced. So we are at the right juncture in your DBA journey where it's time to get serious. Right. So the next part is, why does this module matter? Which is going to be the focus of today's session. I think I'll spend the majority of today's session on the second point. Why should you learn deep neural networks as of 2026? The third part is I will give you the course outline. What are the things that we are going to cover? What would be the expectation? There is going to be a course and presentation, which will be some sort of a project. We'll come to that. And the general guidelines that I would expect in the course and presentation. That's going to be the format for today. Okay. All right. So let's get serious. So we all use conversational agents. We all use conversational agents like ChatGPT, Gemini, Claude, right? What if I told you that the heart of these conversational agents is actually neural networks? And to be very precise, deep neural networks are more complicated, the dinosaur versions of neural networks. So, in a way, what we are going to study during this module is how did we get to ChatGPT over a period of maybe 70, 60, 80 years. From a simple model to something mega, right? Something mammoth like ChatGPT, like your LLM, like a Gemini or Claude, which is capable of doing 100 things. We'll try to follow the journey and we will probably cut short just right before ChatGPT. That will be the overall course because these will probably come in some other module later. When you actually talk about Gen AI, why LLMs matter, how did we get from neural networks to LLMs? That is a part of a different module. I do not want to deep into that. So we will just stop right before ChatGPT, and we will end where the neural networks really, got out of the prison, made a jailbreak, and we just got into the society, right? That's going to be the overall journey. The first point I want to make today is these neural networks are the skeleton of conversational agents. So that's one of the reasons why we should actually be studying neural networks. If we have to understand LLMs, if we have to understand Gen AI, we usually start with neural networks. In my corporate trainings, this 40-hour module or 40, 30, whatever hour module, I usually do it in a matter of probably 1 to 1.5 hours, right? Because the whole training is for 2 to 3 days. And generally, we talk about LLMs, what they do, um, RAG and agents, and we have to go till agent. And for any training that requires agents, we start with neural networks. We start with what is an ANN, artificial neural, and then deep neural network, and then what's a transformer, and that's how we usually go. So if we want, we can talk about this 30-hour module within 1 hour, but that's not the point. Since this is a DBA course and we expect a deeper understanding of these concepts, we are going to talk about the different architectures, the different approaches, and neural networks are the place to start. Okay, so the first reason to study neural networks is our agents are built on this skeleton of neural networks. So the first question which we had today, where somebody asked if I'm making a distinction whereas there is actually no distinction. That's how it is. Actually, it is correct. I'm making a distinction in terms of its usage and application and not in terms of the architecture. The architecture of LLM is still neural net, right? I hope that clarifies your question now. So, what are the expected takeaways of my module? When we say an LLM thinks, we ask question to ChatGPT, it says something like thought for 30 seconds, 35 seconds. What does it mean to think? Thanks. What does it mean to really think? Right? We use these human terms, and that is another approach that we will be taking today. I mean, in this whole module, we will try to convert mathematical concepts into human relatable words. Like, for example, think. I will say learn. The third point talks about what is learning. Right? I will talk about learn. But is an LLM really going to learn as in how we learn? Taking a pen and paper, writing things down, noting down, recollecting. Is that how it is going to learn? So, what does it mean for a model to learn? What does it mean for a model to think? So, we will talk about the mathematical operation, and we will end it, and we will say, okay, in human terms, this mathematical thing which is happening can be considered learning, can be considered thinking. We will try to make that parallel towards, I mean, all through the module. Okay. So by the end of this module, hopefully, you will understand what a conversational agent is. Is it like a huge library, a repository of knowledge, um, or is it something slightly different? Right? Uh, those, if I'm able to drive these points, I think I would consider this module a success. So the core of your AI is prediction. In very simple terms, an LLM is going to predict the next word. Given a sentence, what is the next word? An LLM is trying to predict that. And which is very, very similar to what you learned in your previous module. Your previous module being ML. The core of your ML was to predict, right? What did you do in logistic regression? Given these features, is it 0 or 1? Which is a basic prediction. In your linear regression, given these features, what would be the number on a continuous scale, right? So anything related to AI is going to be prediction. And how do we predict? We predict by understanding the knowledge base, by understanding the quote unquote the features, right? My decision to do anything is based on my knowledge or my understanding of the field and a hope in neural network and generally in the area of AI is that if I give enough knowledge, if I give enough features, the prediction will happen accurately, right? To that effect, to that effect, uh, automation in most of the fields is already here. Be it is a simple automation in terms of assembly, car assembly, or providing emotional support, or self-driving cars, or kind of humanoid robots, bots. Automation is already here, and at the core of it lies predicting the next thing, like in terms of time, what's going to happen next. A self-driving car should predict that if somebody gets into the road, then the next possible task is hitting the person and it should apply the brake, right? So the expectation and taking action is part of the automation. We've always wanted to automate things for a pretty long period of time. And there have always been barriers to this automation in very different forms. Now, if I ask you to think of somebody living in 20th century and identify anything that you would want to automate, what would it be? Can you give me some examples, some one or two examples? Before we got here, maybe 200 years back, we want something automated.
Maybe a
What would
printing.
maybe printing, right? Okay. So what would be the salesperson job? Yeah, maybe yeah, correct. And what would be some of the barriers to this automation? Let us take salesperson job. Now we are having some sort of a product, uh, probably tea, and we are trying to find out if a person will buy tea. Health diagnosis from high entry cost. Okay. Can you elaborate on high entry cost?
Yes, it will take a lot of investments to come up to implement these technologies in businesses.
Yeah.
And when they are unsure about ROI, the return on investments, it becomes even more daunting for them to think along these lines.
Right? Yeah. So how am I going to too many unknown variables, correct? So uh, I think in the context of India, I know there are a lot of global audience. I think this would be a nice history tidbit also. Um, Now, tea was probably trying. People are trying to sell tea in railway platforms as early as I think 1800s or even probably before that. The point is, was railway station the right place to sell storage and compute was the biggest shot for the Junior. Correct, exactly. Correct, yeah. So that's where I'm getting it. Right. So if we take an example, automation, if we want to sell something, if we want to do some sort of sales, the barriers to automation comes in various forms. That could be a problem in technology. That could be a problem in data. We don't know what kind of person will actually buy tea, right? The just the presence of money is it doesn't guarantee that somebody is going to buy a product, right? Um, uh, in terms of automating stuff, do we have the enough compute, right? That is the hardware aspect of it. Um, do we have the real technology in order to sustain the automation? In a lot of cases, we can actually build a model, but sustaining it, keeping it going, actually requires a lot of infrastructure, right? And are we having enough tools and the probably the technology to actually implement an automation? Now, the reason I brought this thing is the field of AI, the field of neural network, has faced barriers in each and every aspect of these four domains, in these four domains, and it has actually overcome. And every time neural networks faced a barrier in a particular domain, people always thought, okay, this neural networks are done. We're not going to gain anything from investing in neural networks. And that is called an AI winter, where nothing really came out of this new buzz and this excitement until something revolutionary happened. The barrier which people faced, they were overcome, and the field of AI, field of neural network, continue beyond that. Our journey in this whole module, security worries, yeah, correct. That is a very modern barrier where which I would put in as a combination of hardware and technology, right? Security barrier. We need both the hardware and also the technology to understand and implement and overcome the security barriers. Correct. So the field of neural network has faced barriers in all of these domains. And every time there was a barrier, people always thought the field is done. But like a phoenix, it always came back more, let's say, came back stronger. And that's how we got to what to where we are here. And that would be the last slide of today, where I would explain the overall journey of neural networks for the past couple of years and how we have really structured this module based on that journey. Okay, so you can think of this as a drama, and we are now in the Act One, where we discuss the capabilities of neural networks. When I say capabilities of neural networks, the capability of not neural network in 2026, but traditionally, when neural networks became a thing, what people really, why neural networks really was popular, why everybody wanted to do neural networks. I think this, I'll just share a very something from my neural network days. I think the year was 2020, not sure. We had a client who had this humongous data set with a number of missing values. And I'm throwing these terms at you, assuming that you're already familiar with these terms. With a lot of missing values, with a lot of um, unnecessary features. It was a huge Excel sheet with uneven data. Some of the numbers were small, some of the columns were text, lot of missing values, a lot of unnecessary columns. When we actually took a look at the data, we we told the client that we can solve this problem in n number of other ways, like using artificial neural networks or using some of the other traditional ML methods. But the client was so focused on CNNs, convolutional neural networks, a very specific form of neural networks. And ultimately, we actually solved the problem only using CNN with the full knowledge that it could have been solved in at least two other ways, using basic neural network or using other ways. Now, the reason I'm telling this is the buzz, right? When neural networks were popular, people really thought it could solve anything. I mean, you can do anything, and it was they wanted to go behind the state of the art. Sometimes the state of the art is only good for as very specific cases. You don't have to use the most popular thing for every other task. Some barriers also include the lack of physical infrastructure to facilitate the development of these core domains. Hundreds of data centers are being built to facilitate the next wave of innovation and to support current expectations. Correct. Yes. Yes.
Sir, Bharti, I just Chandrasekhar. See, my understanding of neural network is having uh, all the activities done by the human brain being automated, being done by a machine or by a software. Okay. Is that the reason that despite not having like you said, the jailbreak happened with Gen AI, right, for the neural network? Is that the reason that this has persisted in various domains and industries? If you can just educate in terms of what led to the persistence of investment in the time in neural network as a capability?
So the investment in neural network has seen ebbs and falls. Like it has seen its good days and it has had its bad days as well. So when you say the capability of neural network and what the neural network is really doing, you can look at it from multiple angles. And in the next couple of slides, by the end of today's session, I think I'll be able to, you will be able to answer your question by yourself, right? The reason being the capability has been very time specific. You said that neural network is still persistent. I'm going to convince you that why it is still persistent, right? Why not use any Gen AI for anything? If that's what you hinted at.
Sure. Thank you.
Yeah. So the capabilities of neural network, as I was saying, the client was very persistent on CNNs. I mean, it is very similar to what we have today, where people come with a problem and then they say, "I want an agent to do this job." And in a lot of these cases, we would tell them an agent is not required for doing this job. A simple neural network can actually do, or even better, an ML model can actually do the job with the right leveraging, right? So why? So what were the capabilities of neural networks back in its uh, prime? Yeah, Dubai. Yeah, Dubai. What's your question?
Uh, well, sir, uh, as you just mentioned that in some areas where ML gives more precise result,
Mhm.
and at at the same time for a similar problem, neural networks doesn't. And what I have seen before coming to this class, I was looking at that what is the basic difference that between these two algorithms could be, because what I have seen that when I deal with the narrow side of problem, I generally prefer to go with the ML. And if my data set is very less or it's thousands of rows, then ML is very precise and it gives the answer for a specific problem. But I come when I see the same problem from deep learning prospect, then I see there are a lot of things it is performing, be it image classification, computer vision, time series analysis. So it looked like that somewhere into deep learning side it is more general in terms of solving a problem, it is more generalized, but in ML side it is very much specific. That's where I see a difference between the actual results when I compare the results that is produced either by deep learning algorithm or from the ML looks way ahead in terms of solving the specific problem, but in general problems deep learning's always going to be master of it. Is that the correct
Um,
understanding that I got?
it's reasonable. It's reasonable to say that. So I would definitely agree with the ML part of it. Yeah, correct. It's domain specific. It's explainable. It has its own good. But the characteristics that you attributed to deep learning, I would attribute it to the mammoth-like networks, the dinosaur of the networks, like your LLMs. The kind of neural network that we'll be discussing here stands somewhere in between these two, somewhere where there is enough automation and there is an enough increase in the capability of the model in terms of what we want the model to do. But also, it is very domain specific. So the good of both the ML, where the ML is is good in a domain and all that, and the increase in the capability, the accuracy, and all that, which you attributed to the neural networks, which I would say is the characteristics of the mammoth neural networks or the dinosaur neural networks like LLMs. The actual neural network is sitting somewhere in between. where it's taking from both. Did that answer your question? Great. Okay. So we have three more questions in the chat. Persistent on what? I'm guessing that what you are saying. Persistent to, and you should carry microphone. Okay. Um, is my voice breaking sometimes? Is that what everybody is
It's
feeling?
it sounded like you were saying CNM, but I'm not getting it. The
Okay.
client was persistent on CNN.
The
It sounds
client,
like.
yes, the client was persistent on CNN. Correct.
What is that? I'm still not getting that.
All right. So it's more like a story, like an anecdote, to talk about what neural networks were really capable of. I mean, how the neural networks were in their prime uh, before they became these really huge neural networks like ChatGPT. So the anecdote that I was sharing was, so a client came with us asking for just CNNs for a particular problem. They gave us a data set, but we suggested that an ANN can do the job, or even an ML with the correct leveraging can do the job. But they were really persistent on using CNNs. Why? Because they
Okay.
were the state of the art. And that's very similar to what we have today, where people come to us asking for agents to do everything. I want to build an agent for this. And sometimes we try to convince them that agents might not be the most efficient way to do this. People just go behind state of the art. The reason that I told that story was because the capability of neural network was really, people imagined the neural networks to be capable of doing everything, right? And that's the first act of today's class, where we will discuss what were really the capabilities of neural networks and why really people went into neural networks from machine learning. That's going to be the first segment, the first section.
Okay. Thank you.
Yeah. So a little bit of refreshing of your previous module. I have a data set here, just two features, feature one, feature two, and I have a label. What kind of problem is this? The label is 0 and 1. I have two features.
Classification.
Identifying a pattern.
Yeah, so like finding a pattern if feature one and two can predict the label. It's a classic classification problem. How can I, if I get a data set like this, just two features, what would be the first thing that I would do?
Trying to identify the correlation and
So just take one feature on x-axis, another feature on y-axis, try to do a plot, right?
yes,
And guess CNN means convolutional neural network. Yes, correct. And we will see what it is during this module. If you don't understand what the word CNN means, that's okay. Great. Is my voice stable now?
yes,
All right. So let's do exactly that. Let us take feature one, feature two, identify what type of data it is. Easiest way to make sense is to plot, right? Now, can linear regression solve this problem? It probably can, right? We just draw a line which probably separates one label from another label. So all these are label 0, all these are label 1. We can draw this line in multiple ways, And if you remember your ML days, it's like a three-dimensional line that goes something like this, where all the yellow dots are sitting here and the purple dots are sitting here, and we are trying to find a cutoff which really separates these into two different groups. This is an extreme data set. Let's not take it too literally. The point is, and logistic regression can actually draw a line which would separate these two categories in a very meaningful way. Now let's go to another type of data. This is a sample data set, feature one, feature two, again labeling. Again, at the outset, it looks like a classification problem. Now let's go ahead and plot it. What do we have here? We have feature one and feature two. How do you interpret this?
This would require ASVM, right?
Yes, something, of course, something more complicated, but can an SVM be a perfect solution for this?
Or in other ways, like it requires a kind of a feature transformation.
Correct. So it's essentially it's a non-linear problem. From a linear problem, we moved on to non-linear problem, right? Where the relationship between feature one and feature two is much complicated than a simple y is equal to or mx plus c kind of a thing. I don't know what terminology you are used to, beta 1 times x plus beta naught, probably, right?
Yes. Yes.
Yeah. So the relationship is slightly complicated. Now, yeah, okay. So the first problem, we had a solution, logistic regression. The second problem, we learned that logistic regression is not probably the best. What is an SVM? SVM is support vector machine. Yeah, correct. Support vector machine, which I am sure would have been covered in your ML module. You can go back to the lecture notes. We will not go into what is an SVM at this point. Okay, the third problem that I want to introduce, we'll talk about the problems first and then the solution later. We have this very famous data set called the iris data set. The point of the data set is the genus iris has three species: iris versicolor, iris setosa, iris virginica. Now, to an untrained eye, all the three look very similar, but a botanist can probably say he will look down on us and probably say that, oh, the difference between them is as clear as day. So we, being in the field of data science, we will say, I will not trust the eyes. I will go only by data. So I ask the botanist for the data, and they give me various things like the length of the sepal, the width of the sepal, which is basically this part of the flower, and the length of the petal and the width of the petal for all these three. And I'll tell the botanist, hey, look, I'm not going to trust what you say. I'm going to see if I will be able to predict it by using my measurements. So I try to build a model, and that is the famous iris data set. I'm trying to see if I can make this classification, this three-way classification, versicolor, setosa, virginica, we just for simplicity call it 1, 2, 3, category 1, 2, 3, based on these four input features, right? Now, if we just take take any two values, the petal length and petal width, petal length and petal width. For convenience, I've selected this. There is more into this data set. So I take petal length along the x-axis and the width along the y-axis, and in a very simple way. To simplify things, basically, I've also reduced the three-way classification into a two-way classification, and I am plotting it. I'm plotting the data set. Again, we can see some. Okay, so we can see some separation between the yellow dots and the purple dots. Ideally, the line can be here, right? Or the line can be the line that I have drawn, or it can be here, right? This is an artifact, ignore it. The line can probably be here as well, right? So there are multiple ways to draw a logistic regression line, but none of them, if you notice, is actually really capturing the real distinction between the two categories, right? So again, non-linearity, there is some sort of a non-linear relationship between between the two features that I'm using to make the prediction. Let's scale the problem a little more. I have a medical image classification problem where so this is the back of the eye called the retina. I'm sure everybody is familiar with the term retina, right? That is where the image falls in your eye and the brain takes that image and does stuff and we are able to see. So if the image is not clear on the retina, you can't see, right? On the right, we have the image of a very typical retina. And in the left, we have a retina that is affected, and it is affected because of diabetes. You know, because of the diabetes, the retina is not able to hold its anatomy. So we see all these real things. Now, how can how can a simple neural network, or how can a simple what to say um, regression problem or an ML model solve this? To us today, it might seem like this problem cannot be solved using ML. If ML is all you have, can you give me some suggestion as to how we can solve the problem? How we can tell if how we can tell if a normal retina from an affected retina? Any guesses? We don't have images, we don't have LLMs, all we have is ML.
We can take various parameters, something like the it could be the pigmentation or any such properties, and then use a principal component assessment, and then try to bring a simplified classification logic.
Yeah, basically, yes. So people were trying to solve image problems using ML for a very long time. So what they would typically do was exactly visual differences. So we do have visual differences, right? So they would identify, they would say something like the redness of the image. Somehow they will come up with a very complicated mathematical formula which will, and this is the job of the mathematicians and the statisticians, who will actually come up with some sigma, some integral of something with a bracket and the differential of something, and a formula that would really give us nightmares. And they would use this and say, okay, now I have a way to find out if there is this yellow spot, if an image has an yellow spot or not, or if the image has a black spot or not, right? And depending on that, they will give a score. So there will be like a black spot score, and there will be like a yellow spot score. or the number of instances of the yellow spots. I mean, if you look at the field of computer vision, it's not actually that complicated. It is reasonably complicated, but you can actually count the number of black spots. At least you can tell if there are two or five, right? Visual different. I'm not sure SVM is covered as per my notes. Someone give the info session WhatsApp. Okay. Okay, yeah, correct. Leon Walsh, correct. So the age of the patient. So we would input all those parameters. Apart from the visual differences, we would go to their medical record, get all this information. Ultimately, just try to build a very basic logistic regression model, right? So that is one way of, but I hope that you understand that it is not a very straightforward problem to solve, right? So great retinal images for these very complicated terms, hemorrhages, X-rays, all these things. Now, if you see, I already mentioned mathematicians, and I also mentioned, and all these terms. Again, this looks more like a spell bee test rather than something that I would encounter in my everyday life. So we would require ophthalmologists help. We would require people from multiple domains. So the sheer complexity of the task, understanding the variability in normal. Now, if you look at this, here we can really tell these two apart and say this is typical and this is atypical. Now, how about this? Right, there are these little yellow spots here. I mean, is it even normal or not normal? We don't know, right? So sometimes not all the retinas look alike. There is something called biological variability, like how we have differences in height, differences in finger length, and all that. Uh, a normal retina can appear in a typical retina can appear in more than one base, right? So it's a very complex task. So how are we going to address that? The fourth problem that I'm going to talk about, and I'll keep it simple again. This is very small. This is also a problem that will be interesting. Yes, Chandrasekhar.
So in a retinal scan for for diabetic person, a scan is taken, right? I'm just trying to understand from a
Yeah.
practical standpoint, and then it is just it's nothing but a picture of your retina, right?
Correct.
That's your first step, and then that's fed into what for? And I've seen it. I've seen it for one of my friends, where it shows up on the screen, and it makes some recommendations maybe on the screen. Okay, so what is happening between uploading the scan report and showing on the screen?
Great. So you've now gone to session, I think 10 or 11 of the module.
Okay, great. Got it. Got your answer.
Okay. Yeah.
Okay,
So
yeah, I'll wait. No problem.
I have a follow-up question.
Yeah.
And can I ask at this point? Yeah. So now you were mentioning, instead of extracting the parameters, if we have an image and if we feed it to a CNN, if it can detect directly, then it is a much more an advanced methodology when compared to tabular parameter extraction and then doing it, right? Now, as you are in the practice of medicine using the neural networks, I have a question.
I'm not. I was in clinical optometry a couple of
Okay.
years back, but now I'm mostly into AI these days. Anyway,
Okay.
I understand enough clinics to, I think, address your
Yeah.
question. You can.
So when a system gets accepted in the medical domain, the explainability and the understanding of the logic being applied is very critical. Now, when a characteristics of an image or a retinal image or any other medical characteristics, when it is extracted in recognizable parameters and when a model getting applied, the trust over the model appears to be high, but whereas the same one, if we feed it to a neural network and it gives the interpretability and explainability is less, and it still produces something, we can for example, like it simplifies the feature engineering. or it recognizes the nonlinear relationships which couldn't be manually engineered, but still it may be challenged to get adapted in the uh, practice because of lack of explainability and transparency. Is it correct, Dr. Siddharth?
That is, I would say that is very accurate. So yeah, the again, I'm introducing these problems considering the journey where you are. You only know ML now, and I'm assuming that using ML alone, can you solve these problems? That's the question that I want to put forth
Got
at this point. That's why I'm talking about all the problems without giving a solution, right?
it.
But I agree with you, correct. So any model which we want to introduce in especially the medical domain, we would expect it to have some explainability, especially if it fails. Like for example, it can become actually a legal problem where a person goes through a screening and then the model says that they do not have a disease, but then 2 years down the line, they are diagnosed with an advanced stage of the disease where it could be very much that the model actually missed. And we might want to go back and see, why the model missed. Why did it say that this person was normal when in fact there was an abnormality? Probably the model will not be able to do that, right? We can't go back. And that's why some of these are black boxes. Right, correct. I agree with you.
Thanks.
Yeah. Okay, so the last problem that I want to flag today is the problem of sepsis, potentially life-threatening, that arises when body's response to infection causes injury to its own tissues. Right? I mean, fairly, I think we know in a very broad level the definition of what sepsis is and why it is a problem. Right? So it's often triggered by injection. I don't want to convert it to some sort of a medical lecture, but the complexity of the situation, right? The goal for us is to forecast the impending sepsis onset somewhere 6 to 12 hours in advance, right? And we are going to use different data that is available to us, things which are continuously monitored, things which are static, a combination of everything, combination of image and all that, where somebody would be flagged as potential for sepsis, so that some sort of an preventive measure can be taken. Now, the data set is multidimensional. So there is age, there is the sex of the patient, weight, height, BMI, what type of ICU service the person is in, which type of admission the person got into. Was it an emergency? Was it a regular ward? Is it from an operation theater? Times, how long the patient has been there, number of all these things. Some of these are basic, some of these are numbers, some of this is string variable. Also, some of these are images. Like for example, some of these data should probably the come from a lab report, which typically is in the form of a printout where things need to be extracted from the printout, right? Some of these probably actually come from a different from the image domain, right? So I'm not claiming that all the things that I say medical are correct, but I'm introducing these to give you an assessment of the complexity of the situation. Imagine each one is a column, and we are trying to build a model which all of this with multimodal data, probably with a lot of missing values, right? And a different types. Some of the scale could be 0 to something, some of the scale should be just 0 and 1. Some of them could be irregular time series, lot of missing values like charting maps, right? So, um, I hope that I've convinced you that this is a fairly complex problem. which ML might actually find difficult to solve. The last is images, handwritten digits from 0 to 9, very famous data set called MNIST data set. We can, as I said in the told in the case of diabetes images before, we can try to solve this by using some manually extracted features, putting them into a model, but probably that's not going to work. I'll now talk about the solution for each of this. Okay, for the sample data set 1, all we need is a circle around this data set, correct? Something like this. Now, what is a circle? You can imagine circle as a different lines, a line like this, a line like this, a line like this, and just those lines are connected, right? Your ANN or your neural network, artificial neural network, is just capable of doing that. Where logistic regression gives us just a line, and ANN is capable of giving us this multiple lines where we say, okay, the line 1 and 2 are not getting added linearly, they are getting added non-linearly, right? And if you are skeptical about this, and for even for the iris data set, maybe a single line will not solve the problem. We need a line that goes somewhere like this, and another line that goes somewhere like this. Now we have captured 97, 98% of the data points where one is here and that is okay, right? We don't expect our model to be 100% accurate. But what we have here is a combination of two lines, right? What we need is more than one line to predict the correct distinction in the data set. So as we increase the complexity of the solution, we would probably try and understand now that a simple ML model is not going to do the job because the data set is complex, and hence the solution is also going to be complex. The place where people went to for this is the brain. We observed how the brain learns these things, and that's how we got inspired to build these things called neural networks. We saw, what's a neuron? How does a neuron respond? How are multiple neurons coming together to do a task? Why don't we replicate that using computers? That was the logical progression, right? So we use the human performance as the gold standard to take things forward. And that is exactly what ANNs are going to do. We are going to not do any manual feature extraction as we did in the ML class, like this PCAs and this manually finding if there is, what do you call that, if there is correlation between two columns, we are not going to do any of that. What we are going to do is we are going to dump all the things that we have into a model, that we are going to build, a model that we are going to call the neural network. And we expect the neural network to, figure things out. Let's say we saw a cat for the first time in our life as a baby. Did anybody really explain to us that, that something was a cat? No, right? They just said, this is a cat, that's a cat, that's a cat, that's a cat, that's not a cat, that's a dog. And then we learn to differentiate between all these objects based on our experience. So when we build a neural network, we assume that if we show enough examples of a particular object, the neural network is going to kind of magically learn the features. So automatic feature extraction and classification is going to be the hallmark of neural networks, right? And that works for the image data also, right? No, doctor probably told a learning doctor that there are 1, 2, 3, 5, 6, 7, 8, 9, 10 black spots, and maybe they learned that there are black spots, the fuzziness of the black spot, the border, it is a sharp border or fuzzy border. All these probably makes a difference, right? And they actually look for that when they examine your retina. But in order to do a normal versus not normal classification, all we had to do was look at enough normal cases in order to differentiate a not normal, right? So that's what we expect the neural network to do. We are just going to dump whatever we have into the neural network and say, figure it out. You learn the features, you do your transformation, and just give me a solution. That's all, right? And the mathematics of the boundary is learned during the training without any manual input. Let me just finish this one segment and then I'll take your question. We'll give you 1 minute. Okay. And did it work? It actually worked. So the performance for a non-linear structured data, typically, I think this is the example of probably um, the circular data set. The performance increases by six from probably 65% to around 96%. I think is the iris data set. Chris, I'm not sure. Yeah. So the ANN, just dump the information into a neural network, let it learn, and like magic, we have a response, right? So the solution for all our problems is neural network. So line one, line two, it figured out, it gave us. Yes. What's the question now?
Yes, I have a question, very
Yeah.
basic question. I just want to make sure I understand. You were using the example of a cat. So in ML, we teach the model what the cat is, label it, and then it generates output based on that knowledge. And you use the example of human brain. So we tell a child it's a cat, and then he figures it out. In neural network, we do some training. I mean, how would it know that these characteristics fit the description of cat? So we have to have fed him some knowledge of what cat looks like. Am I right?
So you say we, do you mean the neural network?
I mean, the people who are creating the model, they would have done some training to neural network to say that if it has four legs, if it has this kind of ear,
Exactly.
so that's labeling. So does labeling happen in neural network as well, or
So
no?
the labeling happens absolutely. Anything in AI requires labeling. Okay, even if it is LLMs, even if it's Gen AI, everything in the field of AI requires labeling absolutely. But what's different in a neural network is we do not manually tell the network that a cat has four legs, it has pointy ears, it has a cute face, right? We don't tell these things, it has an attitude. So we don't tell the neural network these things. We just show the neural network with a label class 0 for cat, label class 1 not cat. And the neural network actually figures everything about the cat by itself, almost like magic,
Okay. Okay, I
right?
think we will learn more
And
down the road to understand it
exactly,
better.
exactly, yes. So the purpose of this module would be to convince you that it's not magic.
Thank you.
So traditionally, the neural networks basically did pattern recognition. It was able to identify images. It was able to identify speech. It was able to identify fraud signals. A classic is credit card fraud detection. So we would show the neural network thousands of samples of what a normal credit card transaction would look like the time of the day, the money spent, the authentication required, the city, everything about the transaction we would send, and we would let the network figure out if a transaction was fraud or not fraud, right? So another superpower of neural network traditionally, sales forecasting, stock risk scoring, any of the things that I have mentioned, you can read this. Spam filter was a very classic neural network thing. When an email comes, spam filter is not a recent one, right? It's been around for a very long time. Medical image diagnosis, churn learning, yes, Nimesh.
Yeah, Professor. Just a question out of curiosity. So, when we say that we dump data into the neural network and the network starts to figure it out, so is it like a time bound thing, or is it that you need a large amount of data for the neural network to figure something out? Like, what are the parameters that are controlling this output from the neural network? Is what I'm trying to understand.
Great. So, give me after the break, I will just actually show you. I'll build a very small neural network and I will explain that.
Okay, thank you. Thank you. Yeah.
Okay.
Professor,
And
one
you
question.
mentioned ANNs. There's one question in chat. I'll come back to you. Mentioned ANNs. It means early models of LLMs. Yes, I won't say early model. I will say a version of LLMs, like the great ancestor of the modern LLMs, right? Yeah, go ahead.
Yeah. So when the EBMs, the energy-based models,
Okay.
can we call that also a neural network? And the reason why I'm asking that is now, though we have an essence of neural network in many of the components, for example, transformer also has a kind of a neural network component, but then it adds some more elements. Now, if we take the LSTM, then it uses a bit of neural network, but the thing is, it uses a lot of gates. Now, in that sense, like we can't say all of them are neural networks, but they have a bit of neural network. Is that understanding correct, Professor?
I I wouldn't say a bit of neural network. I would say um, a version of neural network. You see, I'm actually going to show something that I'm going to build using LSTM, and I'm going to call it neural network. You just call me out, but that's okay. Yeah, so it uses gate, but the core of what we are going to call a neural network is going to remain the same in terms of how it is trained, how it quote unquote learns, right? So, so yeah, the battery I think would still be called the neural network. In its essence, in its flavor, it is still neural network. But we are just adding and we are just creating a variation of the neural.
I understand that's how the course is titled as variants. So these are
Correct.
a variant of it. Got it.
Yes, correct. Yes, Atif.
Is there research going on to make neural network transparent? Is it even possible to make it transparent?
Um, okay. So when you say transparent, I'm thinking in multiple angles. I'm thinking about why, what is the challenge in making it transparent, and why we are probably we do know enough about what has happened. So there's something called explainable neural network, where with enough calculations we can explain why a neural network did what it did. But there is also enough scope for us to lose information once some and information goes into a neural network. We will understand that more during the course. And the short answer to your question is yes, we can explain a lot of what is going into a neural network these days. But there's also a component where we might not be able to 100% explain the neural network. And there's a reason for that, which we will understand during the course.
Thank you.
Now, these were the traditional capabilities of the neural network. But the commercial LLMs came in and they just hijacked a lot of the capabilities of neural network, especially the computer vision capabilities. Like, for example, we discussed the classification capabilities. Like, it's a thing with images, with its NLPs, with the medical image diagnosis capabilities, with the spam filter capabilities. The commercial LLMs actually they took over a lot of these jobs which the neural network was actually very good at, right? What is the time? Is it time for a break?
It depends upon your flow, Professor. If you feel it's the right time, we can have it, or otherwise later also.
Later, I think the session is still 1:10. We only have 1 hour of session left. So I think I'll give a break now and we'll reassemble at 8:05 sharp. Okay.
Sure. Thanks, Professor.
Okay. And I would like to leave it in a cliffhanger and say that, LLM just lost its charm and, neural networks lost their charm when LLMs came into the picture. And LLMs actually hijack. I'm not telling it try to hijack or anything. LLMs actually are much more capable of doing a job which a neural network was actually capable of doing, right? Which basically renders this class redundant. But there's also a twist in the tail, which we will probably see after the break.
Professor, now the LLM, it seems to be a heavyweight, and because of the SLMs are coming in some of the domains and so on, right? So
Yes.
sometimes the LLM will be overkill also, right?
So you should have told a spoiler alert for my story.
Okay.
Okay, so that's where I was building towards. Yes,
Sure.
correct. Yeah,
Thanks, Professor.
thank you.
Can you tell us the duration of the break in minutes because we are not in India?
Oh, I'm so sorry. It's probably 7 minutes.
Thank you.
Right, thank you. Okay, so let's continue. I think that's an example of ML versus neural network. Something in the chat box you can go through. So fraud detection can be done via ML, like linear regression, correct? Probably logistic regression, but yes. Or sales forecast, fraud detection is 0-1 classification. Sales forecast is probably a regression. But yes, I get your question. Do we need DL? Yeah, so it depends on how complex, how many features that we are using. If we are using a lot of features, then probably DL is good to go. Okay, so how the commercial LLMs hijack the capabilities of your basic neural networks. So if you look at the classification problem, right? An LLM can actually do a labeling by using simple prompts. So I would like to take you to a very simple demo that I have created to show this. We share the screen. So for, I hope you can see the screen where I'm showing something like TBA intro to neural networks versus LLM capabilities. Is the screen visible?
Yes.
Yes. So now we have a very simple task. Find the sentiment of the statement. I loved it. It was wonderful. So for those who are unaware of what this part of the sentence means, find the sentiment. A very important application of text processing is understanding the sentiment using with which somebody has said something. This is very useful when we want to do product reviews. So there's a product, the business aspect of it. And there's a product, and then people write reviews for it. Or there's a movie, people write a review for it. So by using the words, can we really say if people like it or if people do not like it? That is what's called sentiment analysis. So we give some text to a model, and the model basically says if it is a positive sentiment or a negative sentiment or a neutral sentiment. I'm sorry about the typo here. As needs to be identified. The second is image classification. The simplest form of image classification is identifying the digit which comes from a very famous Indian data set called the image data set. So we are going to do two tasks. One is an language processing task, and another is an image task. We are going to uh, mm, use the neural network and the LLM to see how the model was able to perform. Right? So I'm sending this text to a neural network that actually I trained using one of the techniques that was just discussed, LSTM. And we have the sentiment here. So it says that it's the positive sentiment. Predicted sentiment is positive. The input text was, I love it. It was wonderful. The predicted sentiment is positive. This is the class probability. Basically, any prediction comes with a probability of it being right. So it says that 99% probability that this text is there's 99% probability that this text is positive, and 0.008% probability that the text is negative. Okay. Now, if I'm going to give the same thing for to an LLM, again, it is doing a perfectly good job. And if you look at how I arrived at it, I have around 2, 3 lines of like blocks of code before I got here. At least 3 blocks of code. 1, 2, 3. Whereas for doing the LLM, it took only 1 block of code, right? So obviously the LLM made the job easy for me. Now the next part is identifying the digit. Like for example, I have this digit. What is the number here? It is 1, the number 1, right? It's a handwritten, somebody with pen has written 1. And this data set is curated based on that. The true label is 1 number. The CNN that I just built, ignore the C if you can't understand. Just understand that this is the neural network's prediction. The neural network predicted that this is number 1. The LLM, again, it predicted that the number is 1. Now, again, if you look at it, the blocks of code, and I used what is called CUDA. CUDA is actually a GPU, which is a GPU is basically what to say? You're again a monster version of a processor, right? So a normal processor probably take a long time to do the job, but I use a CUDA and I use a CPU, and hence the task became simpler. And out of all these blocks of code, the LLM was able to do the job. The LLM was able to do the job in probably 1 or 2 blocks of code, whereas it took multiple blocks of code for me to train it using the neural network. Right? So now, if we, I hope you can see the presentation now, the slides now. So what? So basically, why did this happen? Why did the LLMs take over the job of the neural network? Like you were able to send a text, and suddenly the LLM was able to do the same job, probably with a little bit more accuracy, right? Compare the two approaches. That's what we actually did. And I would go back to that and I would actually show how the LLM achieved the job. Okay, so all I did for the LLM to do the job was I gave the image to it, which is I gave the image to it, and I told the LLM I want a text output. I'm giving a text input and I'm sending an image along with this prompt. I told the LLM this is a handwritten digit, predict only the digit number from 0 to 1. This is all I told the LLM, and the LLM was actually able to give me a response. It gave the response as 1. The digit is 1. Okay. The same, at this point is what's called inference. Inference in the sense, like in a traditional ML, you built a model, right? Now, how will you use the model? When a new data point comes, you use the model to make a prediction. Okay, in LLM terms, you call it inference, but it is basically the same concept. You have an LLM sitting, you give the new data point and you ask for a question, you ask for a prediction. Right? But the setup that I required for doing that, I can come to that in a minute. What I want to do also is I want to show how the prediction happened using the CNN. So again, I am saving the model. Okay. and I'm giving the image input to the model, and it is actually making a prediction, right? So when I'm asking the model to make a prediction in LLM, all I had to do was just give this prompt and probably know this correct syntax to ask the LLM. The LLM that I used was GPT 4.1 mini. For the CNN, again, the way that I'm getting things done using the model is probably quite simple. I wrote a very simple code. I gave the image, I gave the model, and I said, use this model to make a prediction. The setup is very, very similar for the text input also. So again, all I'm telling is analyze the sentiment of the following text, return a sentiment label, a short explanation for why you arrived at that particular explanation. Whereas here, um, these are numbers, right? So it can only give 0 and 1. Firstly, I need to correctly map the 0 to a negative sentiment, 1 to a positive sentiment. Here I did a logistic regression, so only 2 were possible, but I can do 3. You don't have to read too much into the 2 class category. And again, I gave the model, I gave the text, and I asked it to make a prediction. This part you will find that it is very similar to what we did for the image, right? Gave the input, gave the model, asked for a prediction. Most of the arguments are very similar for image and the text. The point I'm making is the way that I'm going to get things done using both these approaches is probably very similar and very simple. Sometimes the I'll show you the output also. Okay, so ignore this epoch and all this. Just focus on the accuracy. The accuracy of the model that I built was 87.8, around 88% accurate. The neural network model is 88% accurate, right? I'm assuming that you know what is accuracy and all that.
Yes, Professor.
Right. So it is around 88% accurate. It's very difficult to get the accuracy of an LLM, but we can say that a powerful model like 4.1 mini is fairly accurate. Even if you give an ambiguous text, it will probably classify it correctly. And the accuracy of the model that I built here is around 97% for the digit identification. At the end of it, I think I got like a 94, 95% accuracy for the neural network that I built. Again, the accuracy can be slightly higher using for the LLM, right? Now, let's go back to the slides and see, does it really matter? This 1%, 2%, 3% in improvement in accuracy, which the LLM is giving, does it really matter, right? Or the non-neural network approach is giving. Now, at this point, I would really like to explain. I'd like to explain the difference between what's called an absolute improvement and relative improvement. So absolute improvement is what is called the real, raw difference. If I say that the accuracy of one model is 92%, the accuracy of another model is 93%, it's very obvious that the increase in the point percentage is 1%. But there's something called a relative improvement, right? So relative improvement is the percentage change over the original. Like what is the real implication of this gain that I'm getting? So, and that absolutely depends on the baseline. For a model which doesn't do anything, which is probably, 0% accurate. I mean, you can't have 0%. Let's say it is 50% accurate for for a two class classification. So by chance, by absolute guessing, if it's a two class classification, it is going to get the classification correct 50% of the time, right? Because the probability flip of a coin 50% 0.5, right? So if if there is like a 5% improvement from the guess rate, that actually means that the model is actually doing something, right? The model is getting there, is probably getting in the right direction. More so, if the model is around 55, 52, 53, and you are actually improving it to 58 or 59, the same 5%. But if the model is already at 90 to 93% and a 5% improvement there could actually mean something else. In the sense, um, you tend to ask if this 4%, no, what is the real world implication of this 4%, and that's where the relative improvement comes into the picture. So the relative improvement is like the absolute gain by the baseline into 100%. So if my absolute gain is 1% over 92%, then my relative improvement is around 1.09%. This number will actually improve if you start around 50, 52, and it kind of saturates the saturates as you go higher, as your baseline improves, right? So how to read this in English is the difference between relative improvement and absolute improvement becomes narrower and narrower as the baseline increases. That's all we need to understand. So in terms of really improving a model performance from, in our case, 87% to probably 92%, and we are talking about a 7% increase, right? So will the relative improvement be like 20 or 30%? Probably not. For a baseline of 90, the real improvement will probably be very close to the absolute improvement. The question is, does it mean that the LLM's performance, can we just brush it aside and say, you know, 2%, wow, how does it really matter? I'm going to show two examples to show that, to make my case for LLM and say, yeah, even a 1% or 2% improvement might actually make a difference at scale. Now, let us think of an ad platform that is running 200 million impressions a day with a 2% click to revenue ratio, CTR. CTR is basically how many clicks. So you see these ads, right? So you click on the ad and it takes you to the ad page. Most of the time, you don't buy it, right? But if you do buy it, then the percentage of clicks that gets converted to revenue is the CTR, the click to the revenue ratio. Now let us say that I build a model which lifts that 2% to 3%, so 1% improvement. Okay, the number is already small. That's a 1% improvement, and the scale is also big, right? So that translates to additional some million clicks per day, and revenue wise, if you do the math, it can come to around 1 million per day. Okay, recording will stop in 2 minutes. Okay, that translates to around 1 million per day, which is not at all a small number. So the 1% increase actually made a huge difference. Let us say we have a neural network that is 2% and LLM which is 3%. Then we might actually want the LLM because the revenue is good. let's forget about revenue for a day and think about something slightly different but equally significant or probably more significant, which is human life. So at a hospital which runs around 500 scans a day, let us look at a model that reviews probably radiology scans with 94% accuracy. Now, a 2% accuracy, uh, if I improve the model's performance by 2%, what it translates to in terms of the raw number of new cases that the new model diagnosis is actually 5, which means that with 96% accuracy, the new model will be able to diagnose 5 more cases if the average is around 500 scans per day, right? Now, that is still very significant, right? So the point I'm trying to make here is a 1 or 2% that the LLM is bringing to the table cannot be brushed aside as insignificant in a lot of cases or in cases where it really matters, right? That's where we open the book and we look at the fine print. We look at the details as to how did we achieve this 1% improvement or the 2% improvement. So how much time did the model train? How much memory did it take? Was there any disruption in the deployment? For a model that is running continuously 24/7, in order to stop the model and to introduce a new model, a whole ecosystem around it, the infra, everything needs to be changed, right? So that is going to probably cause a disruption. And if the company is going to send out an email and say between 1 a.m. and 2 a.m., the service will not be available, right? Global disruption, right? So, what is the reduction in revenue that introducing a new model is actually going to cause, right? If it is going to balance out the 1% improvement, then the next question is it really worth it? Are there any domain specific implications, right? In the very simple case that what is the energy cost of the model deployment improvement exactly, right? So that is, we know how energy consuming the LLMs are going to be, right? If we go back to our example, how did we set this up? I used a GPU, of course, but for doing the sentiment analysis, this is my first import statements. That is okay. Okay, this is again part of my setup. This is actually where I am implementing the model. What you will notice here is I actually built the model from ground up, which means I have complete control over how the model was built, about the data set that I used, about what parameters that I used, what features that I used, right? But how did I arrive at a conclusion from the where is it? From the LLM? You see, I use something called an OpenAI API key. So the API key in a lot of these instances is actually a paid one. So I actually paid for my API key here, right? So, I mean, for my class purposes, I do have a paid version of the API key, right? So, the model is deployed elsewhere. There's going to be a cost component. I have absolutely no idea how the model was built. I don't know how to update it. Whereas here, right? Whereas here, this is the inference where I'm actually calling the model to make a prediction, but I have everything that led me to that point. right? All this led me to here. But all I have in an LLM is this, right? I don't know how I got here, but I know that this is existing. I pay somebody some money and they give me a key, and I just use the key and I make an inference, which is again what I'm doing for my image as well. So all I'm doing here is use a service that is available to me, whereas when I'm actually building the neural network, I know every aspect of how the neural network is built because I am building it from ground up. Of course, I needed a GPU, but I could have done it using a CPU also. It could have taken slightly longer. So this is exactly how I built the neural network. What features go into it? All these are, I know they are difficult terms, but we'll understand every single aspect of this. What quantity means, what ReLU means, what max pool means. That is the point of the course. What is flatten, what is dropout, what is linear. So every word that you see here, cross entropy, um, running loss, all these words that we see here, we will learn during the course, which means if I decide to build a neural network, I have the potential to have full control over what I'm building. Right? If I decide to use an LLM, I only again have a key and I open the key and I just put out my hand and somebody puts an answer in that and I take it back. That's all I know. Right? So, yeah, there was a question. I saw some hand raised for a brief amount of time.
Yeah, it's Samir sir, Chandrasekhar side.
Okay.
So when you're creating your own neural networks, when compared to an LLM, through the open key gives you access to a world of data sets, right? And your neural network, how are you managing that when you are creating it?
Exactly. So the when I access a model through a key, I'm getting access to a whole new world of data set. I am getting access to a model in its bare bones, or in an simplified, probably oversimplified explanation. It is very similar to a model that you would build, what you have built in your previous ML course. You trained and then you built a model, right? So somebody is selling that model to me, not even selling the model to me, is giving me an access to the model for is giving me a one-time access to the model, right? Every time I put the key, I open it, I give the model a data, and then I ask for an answer. It puts something in my hands, I take it out. That's all. Next time I want to access the model, again I open it using my key.
Got it. But when you're doing that, now there's a follow-up question there. So
Mm.
is that when you're taking that approach, you're already
Mm.
having an access to a trained model,
Correct.
correct? So
Correct.
but in a neural network,
Mm.
what are you accessing to get those answers when you're asking these questions?
The
Where is
model,
this going? The same
the
model.
model, yeah, no, a different model that I trained. So here,
Okay.
I know the data set, I built the data set, I have control over what parameters that I used, how much time it took, what will be the time to update the model, everything I have. So if I want to update something in an LLM, there is I'm not having many options, right? I'm not giving a gray
Understood.
black and white answer here. I'll come back, circle back to this in a while.
Sure.
Yeah,
Sure.
Aleph.
Yes, I have read in articles that they say that this model is built around LLM capability. So, so is that sort of like a right way to think about it? It's a hybrid of LLM and neural network?
An LLM is a neural network,
Yeah, they in finance world
right?
I often hear, oh, this is specialized neural network, but it's built around
Correct.
LLM capability.
Yes, so it could be multiple things. It could probably mean it was fine-tuned on an LLM, or it was a neural network, or yeah, it could be different things actually. If you can bring me the exact words, maybe I can explain what probably happened in the backend.
Okay, I'll share that with you there.
Sure. What are the must-have elements of an LLM? Elements of an LLM that you're building in simplest of us. Great. So what did I use to build an LLM? I just LLM or neural network? What was the question? Sorry. It was must-have neural network. Elements of neural network. So I'll just go to that thing and I'll show what I used there. I'll explain using the text data set because it's simpler. Okay, leave all this. This is the part where I'm loading the data set. So I need a data set, a reliable data set, a huge data set. Next, the same training and test split that we have used in the past in your LM, in your ML, right? So there was this data set, ability to split it into train and test, and some basic ways to convert words into numbers because computers understand only numbers. So we convert the words to numbers in some way. And if you look here, CUDA, again, it's a GPU. So I need some sort of a hardware setting where I can actually train and I tell how to train it. That's all. I'm defining my training methodology and here I am training. So to put it in simple words, I need a data set, I need an infrastructure to train, um, and knowledge of neural networks to know adjust the parameters and get the best out of it. Yeah. Right. So now we saw the whole cycle where LLMs were great at doing some things, and then neural networks were great at doing a few things, and then the LLMs they really came into the picture and they kind of hijacked the capability. So people for even now in a lot of situations, they do sentiment analysis by using LLMs. They call a model and they do sentiment analysis, which is fine, right? But think about the implications. Think about everything that we are going to consider while implementing a model, and that's why LLM neural networks are still relevant in 2026. Not just to understand how LLMs work, or just to understand the architecture in a theoretical fashion, because I think in my third slide or something, I mentioned that the skeleton of conversation agents is neural networks. I told this is the first reason to study neural networks. Now, that's a very theoretical reason, right? Yeah, yes, it is like learning tables. I know that at some point, every kid in the house has asked, why do I need to read tables? Why do I need to memorize the multiplication tables when I have a calculator, right? And we always say, yeah, the capability of the tables is different than that of a calculator. So this is something like that, right? Where where uh, we are going to say that yeah, neural networks are there, LLMs are there, but neural networks are still relevant, not just to understand the theory behind the LLM architecture, but neural networks are actually more efficient even in 2026 to do a few jobs which LLMs can actually do, right? So that's a question. Nowadays, LLM is not just a chatbot, it's an agent, consists of multimodal, can connect to different tools, build a model to do the work. Am I right? To build a model, I'm not sure. And I'm not sure if it would be prudent to let an agent build a model. You can, as we have been discussing, build a model and infer from the model. An agent can absolutely infer from an existing model. Yes. Okay. So that is why neural networks are still relevant in 2026, right? Mainly, okay. So mainly a neural network is lightweight. Why am I getting a poll now? Are we at the end of the session? I think we have half an hour more, right?
Yes, usually this comes in between.
Oh, okay. I'm not going to answer that. Okay, now I'm going to take the poll. Okay, nice. So LLMs are massive. We'll come to this word called parameter in a while. Let's not worry about that for now. But LLMs are largely general purpose, which means that they can do 100 other things that we don't really require. Um, they are very resource intense, which means that deploying is going to take a lot of infrastructure and setup and all that. They have increased latency. Latency in the sense the time that it would make to make an inference. The model that I used, it was able to make the sentiment or the image classification in a matter of seconds. But if I have to do the same job using an LLM, I'm going to have to take a key. It's going to get an access to a server somewhere, and then it's going to get a reply. So the latency is going to be more. The real-time capability of the neural network is always high. It is lightweight and efficient in its design, which means that it can actually do things in real time. So even if an LLM is good at fraud detection, we need to do the fraud detection in real time during the transaction, right? So that sort of capability, that sort of implementation is possible only with something that is lightweight and efficient, such as the neural network. So, neural networks, models built using neural networks are still relevant if the priority is high speed, reduced footprint, and more control over your data, right? So, another reason for using your neural network is cost and the ability to customize. Neural network is the mother of LLM. You can absolutely say that, yes. Can we say neural network is the mother of LLMs? Yes, you can. Okay, so every inference is going to take a cost, is going to be expensive, whereas with neural network, the time to train might be high, but during inference time, it is probably just a basic setup where this model is sitting, is being hosted. It's only that cost, right? So it is a very low cost implementation. It works. This will probably not make a difference when the number of inferences per day is less, but when you have thousands, tens of thousands of inferences per day, even if one inference is going to cost probably 50 cents, 10,000 inferences is going to be $5,000, right? So, yeah, so those are the things that we would really consider. So still, even in 2026, neural networks are scalable, are cost efficient. We can have more control over the data and the training. Um, I don't want to oversell 1 minute, Deepak, I'll come to you. I don't want to oversell neural networks, but at the cost of LLMs, of course. LLMs have their own capability. We saw what a 1 or 2% improvement in performance can do, and that is absolutely real. But where neural networks shined a couple of years back before the LLM, they still shine in those areas still, right? Maybe some of the capabilities LLMs are able to do, but the scale at which your neural networks can be deployed and employed still has a very special place in modern AI architectures. Yes, Deepak.
So, just a question in terms of like the specific sector. I mean, it may apply to other sectors also. I work in the financial services sector. So, data confidentiality is like a primary like concern there.
Right.
So, in that sense and in that context, do you think like we also use Claude, as like an LLM? But in the context of how we are explaining this, does
Mhm.
having a custom neural network have that much more benefit when compared to like using an LLM for making sure data is secure? Customers are also very particular about having data secure. So is that like relevant in when you say okay, neural networks applies gives you those benefits when compared to an
Absolutely.
LLM? Okay.
Yeah, absolutely. So the especially a combination of the LLM and the neural network. So remember, when we make an inference, every time I made an inference call in my example, I actually exposed my data to a model which is sitting hosted somewhere in a server in a different country, I don't know, right? So I have no idea where that data went for it to make an inference. And any of these commercial models, they absolutely have a log of what comes in and what went out. Okay, because that is required for their legal purposes, for their legal guardrails. If somebody says that I asked this model and it gave this and then it was incorrect answer and it needs to go back and verify if what I'm saying is correct or not. So it might not use the data in terms of for its training or anywhere, but it absolutely collects your data and keeps it somewhere for very basic, very legal and rational purpose of keeping log, right? So exposing your data is not a small thing, right? So in that situations, yes, absolutely having an LLM and building on top of that LLM with your own custom data, posting in your own server, sending your inference to that server and getting an inference is completely a valid approach. That is one of the reasons why you should still learn about neural networks, even when LLMs can do majority of the jobs that neural networks can actually do. That's another question. So a company's build RAG. Yeah, Deepak, I hope that answered your question. I quickly moved
Yes,
away
sir.
from that.
Yeah. Thank you.
So it's why companies build RAG, right? It's when you say it's why, what's why? I didn't get that question. Okay, I'll come back to that question. Okay. So that the strength of the traditional neural network is still there. It is cheap at scale, it's controllable, it's deployable internally, and it has a very predictable behavior. Um, that doesn't mean that neural networks are 100% explainable. I want to say at least it's predictable in terms of, I know what to expect from the model because, I built it. It's more controllable in that sense. Okay, so tasks where the neural network could still win in 2026, real-time fraud detection, where LLMs, remember, if you have to make something to an LLM, it has to go through multiple layers go to a server, get an inference, and then come back to it. When a transaction is happening in milliseconds, that could mean really slow, right? Quality control vision systems, like in terms of factory lines. Again, this is a question of time, right? There's a factory line and items are going like moving really fast on a factory line. And let's say I want to detect a crack in a bottle. I can absolutely send the video to an LLM which is continuously running, but that's an overkill, as somebody mentioned in the start of the class. So defect detection still it's a computer vision problem, and a CNN built for that purpose hosted locally is still a win. Facial recognition at an access gate. The LLMs are absolutely great at face detection, right? But it's a edge hardware where it needs to be running in your CCTV camera, basically on your head edge hardware. So getting access to a cloud infrastructure, routing it through that might be a real problem. So again, CNN's neural networks win there. Medical image recognition, we just discussed that. Optical character recognition, especially identifying numbers, digits, all these things. We saw even with a very small network, we obtained like 97% accuracy. So there are ways to improve it to 98, 99% accuracy. So digital identification, alphabet identification, all these are really good. Wake word detection, all the neural network needs to do for a wake word is when a sentence comes, it needs to classify into binary classification. Is it a wake word or is it not a wake word? Because it is always listening to what we are telling, right? What we are speaking in the living room, when in a Siri or in an Alexa or whatever. But when I say Alexa, it does for every word, it does the classification. Every sound does a binary classification. Whereas Alexa should trigger this, whereas not Alexa should trigger another dot, right? So this should happen again real time. It's always happening. So neural network is much more efficient because it needs to run on the chip and everything. Again, object detection, very nuanced application. When an object comes into the road, if the road is empty, an object comes, the brake should be applied immediately, right? So the inference should be less than 10 milliseconds. So LLMs are still slow in that world. So neural networks still win in that as well. Payment critical urban generation allowing companies to use their own data and internal LLM model. Correct. So RAG is built purposed for that exactly. Correct. So a RAG, the system is hosted locally, and you can use a local model, and nothing ever needs to leave your server to maintain the confidentiality. Correct. Okay, so with this introduction, I think I have convinced you that neural networks are absolutely necessary to study even in 2026. Even in the world of LLMs, where LLMs are popular, neural networks have their own place, right? So the idea of neural network really started in 1943. So that is what, 60, 70, 80 years probably. And then there was this concept called Hebbian learning, where again, all these are from the neuroscience world. So people started exploring how the brain works, how the brain learns really, and how much of this can be mathematically modeled. Um, so yeah, it went through all these stages. We will look at some of the real milestones, and the course is structured following almost the journey of these neural networks. So I think the first couple of modules are the question of perceptron, and then I think the third session is on back propagation. And then the third, fourth session is on multi-layer perceptron. Meanwhile, LSTMs are coming, and then it's 1998, and some early version of CNNs are coming up. And then in 2012, really, this made a huge impact. And we will see all of these milestones. So this is CNN, and then probably we'll bring in LSTM after this. And then the resonance came into the picture. We will probably stop with this, okay, in this course. So each of the things that I have circled is probably one chapter in this module. All right. So I will not end here. Please don't be happy. So I still have the walkthrough of the module. So I hope that I have convinced you that neural networks are not just theoretical. For you to understand LLMs, you need to understand neural networks, but that's not really the course. LLMs have their neural networks have their own place even today, and that's what we will see. So we will start with the absolute basics in this module, where we will start with from perceptrons and its limitations. That was supposed to be today's lecture, but we can quickly cover that in the next lecture. Move on to what are called MLPs or multi-layer perceptron. Yes, Don. What's the question?
Hi, sorry. Thank you. My name is Win, and I'm just out of curiosity. So since NN is the model of LLMs, so is it? I wonder, and I feel like the difference between LLMs and NN is first is the speed, and second is the cost, and third is the know-how of the persons using it. But if one of these barriers getting lower and lower, will LLMs ever replace NN? No, I mean, NN is the mother, so it's just the concept of everything, right? But ultimately, will LLMs replace everything? I'm just out of curiosity. Thank you.
That's a very nice speculative question. Yeah. So when I say mother of all the so you can say that the LLM is a monstrous version of the LLM, right? That doesn't mean that the basic version is obsolete. The neural network in its in its core form is still capable of doing a few things. And the question also comes down to, can you use a sword to cut vegetables from your garden, right? And you can absolutely do it, right? And it's probably efficient when you don't have to carry a pocket knife and a sword, right? We can use a sword to cut the vegetable. That's absolutely possible. And the question is, do we really want to get there? Do we really want to spend our time and resources optimizing the sword to cut vegetables when we already have the pocket knife? Right? Yeah. Okay, so we will move on to what are called MLPs, multi-layer perceptron, and the concept of parameter. Uh, and then move on to the core ideas of back propagation and how, like, the culmination of all this work resulted in a recent Nobel Prize, actually. So we will talk about the milestones which led to the Nobel Prize a couple of years back. Um, so how do we go deep neural network from a simple neural network, and then move to what are called embeddings when we deal with the text data. Okay. When we deal with the text data, and then we move on to how vision is handled in neural networks. How do neural networks see things the way that we see things? Um, that will be a couple of lectures. We deep dive into convolutional neural networks. And then we will really go into the architecture of LSTMs and what are called RNNs, recurrent neural networks, and look into that. And then we'll look at some generative aspects. Like these neural networks can be trained to generate images from scratch. So, like it's like identifying what's there in a canvas is one thing, but painting a picture on an empty canvas is a whole different talent, right? So, what version of what variant of the neural network is capable of doing that? And finally, end with reinforcement learning. The last one or two classes, lectures will be presentations. The presentations will be likely group presentations. What I would expect I'll give a detailed expectation of what I expect, explanation of what I expect in the presentation. But the general overview is that it will be a group presentation. But I would expect everybody to work. I know that implementing that could be a challenge. It's absolutely important for you to show up in the class and be a part of the presentation. So if your group is presenting, even if you have something very important, I would expect you to log in and stay for those 10 minutes, 15 minutes. If that is going to be a challenge on that particular day on which presentation is scheduled, I'm open to moving that group's presentation on a different day, like move it ahead, and we can have it. But it is absolutely important for you to show up and be a part of your group's work. I would expect everybody to talk in the presentation. In the sense, if it's for 20 minutes and if there are four people, I would expect maybe approximately 5 minutes from each person in the group. In spite of this, if you are unable to show up to the class, I would expect a video recording of the part that you were supposed to present during the group presentation, right? So I'll give all these guidelines and details in a while. Mm, but the presentation should mainly focus on the neural network implementation. I do not want anything complicated. I do not want LLMs. I do not want any great architecture or anything that is beyond the scope. But it should absolutely include a component of neural network, um, a named neural network, like LSTM, RNN, CNN, something like that, to be a part of your project, right? More details about the project I'll share later. I think that's the end of the session. Any questions?
Apart from
Yes,
the
Nimesh.
final presentations, will there be any assignments?
Um, I haven't really thought about that, but I think last time I did not have any assignments. It was only the presentation.
Sure. And groups we can choose ourselves, or it will be allotted by.
Um, and last time people chose their own group. So I think I'll stick to that.
Sure. And how many members per group?
I'll give those details later. Maybe I mean, depending on the class, the cohort strength, right? So I'll talk to the relevant people and I will give you the
And what kind of topics you expect in this presentation, Professor?
um, something that uses neural network. So you should come up with a project that propose something that has neural network in its heart. I'll give the details later.
Sure.
Yes, Nimesh?
Yes, Professor, I had a couple of questions here. So, first is on the lab sessions. Are these one-off sessions or are these going to be repeated?
What do you mean? One of
So,
repeated?
when we were doing the foundations of AI/ML at that time, the lab sessions were repeated 3 times. So,
So yeah, there are 3 lab sessions and different topics will be covered in each lab session. That's what it is.
so there is no repeat of the lab session.
No.
So, and this lab session will be around which tool? Like earlier we did Power BI and Azure ML. So,
Um, I didn't do the labs last time. Somebody else did the labs, but I'll ask what was done last time. I'll probably repeat the same thing. Or if you're comfortable with the collab that I showed, minimal coding collab, we can probably do that as well.
yeah,
I'll
just
probably
because,
give a code and you can. I'll give you some parameters to adjust. Just enter the number here, there, make some modifications, and um, just run it. So I'll have a word with my grad colleagues and I'll let you.
yeah, the reason of all these questions were that we had some difficulties because just to IT related issues when we started the first
Right.
lab session, right? So if we could figure
Right.
that out in advance, that would be of help to all of us.
I agree. I
Yeah.
agree. So I faced similar difficulties in my previous lab session. I think I did Azure once, and setting up took a lot of time. I mean,
Yeah.
that is a common thing in any lab session, in any corporate setting, but we navigated some.
Okay. That's all. Thank you, Professor.
Yes, do
And
that. Mm.
uh, so, any specific study material recommendation from your side to go more in deep? Because I understand covering the concepts in just 20 in just sessions, it won't be possible for us. So, is there any specific course material, or you think that I should we should go ahead with that to have a deeper understanding of it?
So I think the course description or the module description has a few reference textbooks, like Deep Learning by Young Fellow. That's a good resource. I think I've referred it a couple of times.
Yes,
So
yes, I saw that. Even I have gone through with some books which are already referred there, but those are those are holding too much of details. I understand these details are relevant, but considering that we all are working and having a major portion of our time goes into our office, and so I want something that gives me a reference wherever I'm stuck, and then taking a some idea out of it, and then go ahead with the hands-on practice.
I'll try to find something. So mostly it will be blogs and mm, other write-ups, because for the kind of depth that we would expect in a DBA class and a DBA session, I think there are enough blogs and other write-ups which are relevant. So I'll try to find something, those
Perfect, sir. Perfect.
slides.
Thank you.
Professor, the course outline which you have shown today and the slide deck, you will be uploading to the portal, right?
Yes, something like if not me, you will be given the course outline.
Okay.
Or if it's not shared, I'll share it.
Yeah, we have a few of us have difficulty in seeing this session online. If you could share it through mail or something, it would be great.
Sure. Thank you.
What are the tools we should, will it be Google Colab or would we need any LLM APIs required at this point of time?
See, the one thing that I want to make sure now is the talk about LLM is probably going to end with today's session.
Mm.
The reason I kept circling back to LLM today was I keep getting these queries in my trainings, corporate trainings, everywhere that, should we really understand neural networks? Are CNN still relevant? Are AI still relevant? Especially when we are doing a 40-hour, 45-hour course module on neural networks, you guys should not feel that we are looking at a concept that is outdated and that is replaced by something more efficient. So that is the reason I kept circling back to LLM. I kept maybe making the comparison. And I think I convinced you that neural networks are still relevant. So I'll not talk about LLMs hereafter. It will be always fully neural network oriented.
So Jupyter with the TensorFlow should be good enough for.
I think so, yes. Yes. PyTorch, TensorFlow, yes. Or Colab, I think is good enough for us. I'll see what was used last time. I'll probably stick to that. All right, then. If there are no questions, I think we can end the session. It was, I think it was a great first session from my side. I hope you guys feel the same way. If you have feedback, please let me know directly. You don't have to wait till the end of the session or wait till the end of the whole module. That would keep things clean between the two of us. Right.
Can we
Thank you
get your
very
email?
much. Okay. I will just type it out. Mm, So you can use both of these emails. The second one is preferable. All right, thanks everyone. Have a good night or rest of the day.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.